problem what we already solved. The same problems we are considering, then we will we will finish it. Whatever we have doubts in our mind, and all these things will be rectified now. The same problem, okay. Before this session, what we will finished, the same problem I am taking, okay. Now, before we start the problem, I just recollect a few points for the previous problem. Effect of adding a zero. Effect of adding a zero. What happens when you add a zero? What is our observation? We want to see the observation with root locus diagram. Okay, effect of adding a zero. Now the root locus branches are completely shifted to left hand side. The first point is the root locus branches are shifted from right hand side to right hand side to left hand side. The root locus branches are shifted from right hand side to left hand side such that stability is improved. The branches are completely shifted from right hand side to left hand side such that the system stability is improved. Okay, this is the effect of adding a zero. So when you add a zero, then students are asking a doubt. Sir, you are adding a zero in open loop transformation. Now which stability is improved? 100% this is a closed loop control system stability such that closed loop control system stability. Now why? Because you are adding a zero in the open loop transformation. After converting into the characteristic, it is totally a closed loop pole. This is the moment of closed loop pole. Whatever we are drawing the root locus diagram, the root locus is nothing but a moment of the closed loop pole. Okay, this is the effect of adding a zero. And one more point, plus or minus 180 degrees by n. This is the angle. This is the angle the root locus branches, this is the angle the root locus branches leaves or enters the real axis. This is the angle where the root locus branches leaves the real axis or enters the real axis. What is this n? Where n is number of poles or number of zeros. Number of poles or number of zeros. Number of poles or number of zeros at break point. Okay. Now this is the effect of adding a zero. While you add a zero, then the branches from right hand side shifted to left hand side, stability is improved. Now this is the angle the root locus branches or leaves or enters the real axis. Now see here, at this particular break point, there are two poles. Therefore, the leaving angle is plus or minus 180 degrees by 2 plus or minus 90 degrees. Okay. If there are two zeros, so the entering angle is also plus or. That's why this is plus 90 minus 90. After leaving, it will follow the angle of asymptotes. Okay. Now these are the angle of asymptote. Clear or not? Now here we have to be followed a few rules and regulations. Okay. So this is a very, very important point. Okay. Just note down 1 second. Okay. Now we will see whatever the doubts in our mind, we will clarify with this problem. That's why just take one problem and I will clarify all your doubts. Okay. Right. Now the first important point, sir, these two closed loop poles are meet at a particular point. That particular point is called as breakaway point. What is the procedure of calculating breakaway point? Okay, now I will give the procedure. Okay. Now, steps to calculate break point. See here, break point or breakaway point or break-in point, all are comes under same. This is the procedure of calculating breakaway point and this is the procedure of calculating break-in point, same. Okay. Now, step 1. Now the first step is find characteristic equation. Find characteristic equation 1 plus g of s equal to 0. The first step is find characteristic equation 1 plus g of s equal to 0. 1 plus g of s is nothing but k by s into s plus 2 into s plus 4, because this is a root locus diagram for which problem? Now this is g of s which is equal to k by s into s plus 2 into s plus 4. Now what is the characteristic equation? Now the characteristic equation, which is nothing but s into s plus 2 into s plus 4 plus k equal to 0. Now what is the characteristic equation? The characteristic equation is s cube plus 6s square plus 8s plus k equal to 0. This is step number 1, characteristic equation. Okay, first step. Now step number 2. Now the step number 2 is write the k value which is a function of s. Write the k value which is a function of s, which is very simple. K which is equal to minus s cube minus 6s square minus 8s. Write the k value which is a function of s. Now the third step is differentiate k with respect to s equate to 0 and find roots. Now differentiate k with respect to s and find roots. dk by ds is equal to 0, which is nothing but minus 3s square minus 12s minus 8 is equal to 0. Therefore, 3s square plus 12s plus 8 is equal to 0. Now, this is the k which is differentiate with respect to s and find roots. And this roots will give valid breakpoint or a valid breakaway point, and this root also will give invalid breakaway point. So keep valid and neglect the invalid. First you find the roots. This is a characteristic equation of order 2. You can easily find the two roots. If you find the two roots here is one is minus 0.8, another one is minus 3.14. Now tell me which is a valid and which is invalid. You already know that this is one pole is at origin. This is one more pole is at minus 2. Between these two poles there is a root locus branch. Definitely there exists one breakaway point. So 0 to minus 2. Therefore this is the valid breakaway point. This is the valid. And see here, minus 2 to minus 4, is there any root locus branch? No. Between minus 2 to minus 4, no root locus branch, nothing. So, and the root locus branch is there, then only there is breakaway. No root locus branch, no breakaway. Therefore, this is invalid. This is invalid. You don't consider this and you consider only this. Okay. This is the way, this is the procedure of calculating breakaway point or break-in point. That's what I'm writing, break point. Okay. This is the procedure of calculating breakaway point or break-in point. So now, pole is moving. As k is changing, closed loop pole is moving. As k is changing, closed loop pole is moving at a breakaway point of, now the breakaway point s equal to minus 0.8. Now this is the breakaway point. At this particular point, these two closed loop poles are leaves the real axis, and this is the procedure of finding a break point for any particular problem. Okay, but in the examination, in the options, if the given, so what is breakaway point? And there are 4 options. Don't do all this procedure. What is a simple solution? The breakaway point or break-in point must and should lies on root locus branch. Some of the options between minus 2 minus 4 is the wrong option because there is no root locus branch. Now the option which is always lies on the root locus branch, in that way also you can rectify which one is correct and which one is wrong. Okay. Now this is the procedure. Note on this. Okay. Now this is the procedure, but this procedure is sometimes not required. Okay, because the breakaway point is always on the root locus. If then the GATE examination some Objective questions are also available. Some fill in the blank questions are also available. So in that case, use that. Otherwise, options are available. Breakaway point must should lies on the root locus branch. You just simply identify the pole's location. First, you just draw the root locus branches. Which section is the root locus branch? Now, in that particular section, only the point you have a breakaway point. Okay, this section is not root locus branch. Therefore, there is no chance of break point. But in options, any value between -2 to -4 is the wrong values. Okay. Now this may be one question. Sometimes he asks what is break point or breakaway point or break in point, like that he is asking. Now there may be another question. That question is nothing but, now I will take a question by question. Now there may be another question. Determine system gain at break point. What is system gain at breakaway point, or what is system gain at break in point? This may be another question. What is the system gain at break point? Now, what is break point here? Break point is nothing but breakaway point, which is -0.8. Now, this breakaway point is lies on the root locus branches or not? Yes. If it is lies on the root locus branches, definitely it will satisfy the angle condition or not? Yes, definitely it will satisfy the angle condition. If the angle condition is satisfied, you use the magnitude condition and to find the system gain. Am I not? We can find the system gain K at any particular point by using magnitude condition, provided that particular point must and should lies on root locus branches, which means it will satisfy the angle condition. Okay. So this is a root locus branch. You cannot find the system gain K by using magnitude condition at this particular point, because this is not a root locus branch. It not satisfy the angle condition. Understand or not? So magnitude of G of S, which is equal to 1 at breakaway point of S equal to -0.8, which means that K by -0.8 plus 2, 1.2, -0.8 plus 4, -0.8 plus 4, 3.2. Now this is the magnitude which is equal to 1. Therefore, K divided by square root of A square plus B square, 0.8 into 1.2 into 3.2. Now this is the system gain, which is equal to 3.07. This is the system gain at breakaway point. Now K equal to 0, K equal to 1, K equal to 2, K equal to 2.5, K equal to 0, K equal to 1, K equal to 2, K equal to, when K equal to 3.07, when K equal to 3.07, these two closed loop poles are meet at a particular point. That particular point is -0.8. At that particular point, gain is 3.07. Okay. Now this is simply by using a magnitude condition. You already know that. Okay. But only one simple note is nothing but the magnitude condition is applicable only when the angle condition is satisfied. Angle condition is in turn it's satisfied because this particular point lies on the root locus branches. No doubt. Okay. Now I want to ask another question in the same problem. Now as k is changing, closed loop pole is moving. When k equal to 3.07, closed loop poles are meeting at a particular point. That particular point is nothing but a breakaway point. Now when k greater than 3.07, what happens? Now the closed loop pole leaves the real axis. Is it right or not? When k is greater than 3.07, closed loop pole is leaving. Yes, closed loop pole leaves the real axis. Now k equal to 3.5, k equal to 4, k equal to 5, k equal to 6, k equal to 7. Now the question is, now what is the value of k when the root locus branches intersects with imaginary axis? What I'm asking? What is the value of k when the root locus branches intersects with imaginary axis? K is changing. At one particular value of k, the root locus branch touches the imaginary axis, intersects the imaginary axis. Now, when the root locus branches intersects with imaginary axis, what is the k value? What is the value of k? Okay, what is the value of k? Now, when the root locus branches intersect the imaginary axis means pole is on imaginary axis. When pole is on imaginary axis, system is marginally stable. When system is marginally stable, this is called as k margin. This is called as k margin. And system is marginally stable and frequency of oscillations are also available. Now I want to ask, what is k margin and what is the frequency of oscillations? Now the question is another question. Determine k margin and frequency of oscillations if the root locus branches are intersect intersects with imaginary axis. If the root locus branches are intersects with imaginary axis. The root locus branches or intersects with imaginary axis. What is k margin and what is frequency of oscillations? Any idea? So this is the first time you are heard a word about k margin? No, the k margin frequency of oscillation n number of times we are calculating. So now see here. Now the solution is nothing but by using RH criteria. This is already solved by using Routh-Hurwitz stability criteria. So whatever you want to do it in Routh-Hurwitz stability criteria, we required a characteristic equation, but the characteristic equation you already calculated. Now this is the characteristic equation, and which is very easy because this is the characteristic equation of order 3. If it is order 3, what is the k margin? When the system is marginally stable, for marginally stable, internal coefficient product is equal to the external coefficient. Therefore, k equal to 48. When k equal to 48, this is k margin. When k equal to 48, system is marginally stable. Therefore, this is called as k margin. If the system is marginally stable, to find the frequency of oscillations, we want auxiliary equation. Auxiliary equation is nothing but even power of s term, 6s square plus k equal to 0. Therefore, 6s square plus k margin, this is the k margin, which is nothing but 48, which is equal to 0. Therefore, s square plus 8 equal to 0. Therefore, s equal to plus or minus j into root 8. Therefore, s equal to plus or minus j omega. Therefore, the frequency of oscillations, which is equal to root 8 radians per second. The frequency of oscillations, which is equal to root 8 radians per second. Now, when the root locus branches intersects with imaginary axis, system is marginally stable. Note down that. Okay. Now once this K margin is identified, you can easily find the conditional stability. What is the conditional stability concept? The range of K such that the system is stable. This is the conditional stability. Now what is the conditional stability? This is the range of values of K such that the system is stable. That particular stability is called as conditional stability. Therefore, when K is less than K margin and greater than 0, such that this is a stable condition. Is it right or not? This is the stable, which means that K is less than, what is the K margin? 48, less than 0. This is the stable condition. Now you can easily find unstable. What is unstable? When it will enter into the danger zone. When K greater than K margin is unstable, which means that when K greater than 48, system is unstable, marginally stable. When it is marginally stable. Now, when K is equal to K margin is called as marginally stable, which is equal to 48. Now, this is the range of values of K such that the system is marginally stable, unstable and stable. This particular stability is called as conditional stability. You know that, okay? But now you can easily understand here if one thing is identified. And another thing is which is very, very important. Now, what is the range of values of K? What is the range of values of K such that, now the question you just concentrated, what is the range of values of K such that the root locus diagram is said to be overdamped, underdamped, critically damped? When this root locus diagram will become overdamped, when this root locus diagram will become underdamped, when this root locus diagram will become undamped. Now, what is the range of values of K? This is very, very important question for the GATE examination point of view. Okay. Now, see here. If you want to answer this question, first you want to know that what is overdamped, underdamped, critically damped. That is not the time domain analysis. That will be there everywhere. Okay. So, now I want to check for overdamped. When the root locus diagram is a overdamped response. All responses, all overdamped and underdamped response are stable response. If the pole's location is like this, if the pole's location is like this, then that response is nothing but the overdamped response. And this is the system is stable now. And this is the dominant pole. And this is the insignificant pole. If pole's location is like this, then we can say this is the overdamped response. Now the question what he is asking is, when the root locus diagram will be appear like this with respect to breakaway point gain or with respect to break-in point gain. Let us assume this is the gain at breakaway point. So this is the gain at breakaway point. Let us assume this is K1. Okay. This is the gain at breakaway point. Now let us assume this is K1. Once again I want to say the question. When the root locus diagram is overdamped, underdamped, critically damped, what is the range of values of K with respect to gain at breakaway point and with respect to gain at break-in point? In our question it is gain at break-in point. There you find gain, that is assume K2. Breakaway point, there you find gain. We already find that gain is K1. So with respect to K1 and with respect to K2, he is asking the questions. Okay. So when K equal to 0, where is pole? Pole is at origin. If the pole is at origin, it is not a overdamped response. If the response should be overdamped, poles must be on the negative real axis. So when the pole is on the negative real axis, when the system gain K is greater than 0. So when system gain K greater than 0, pole is shifted from origin to here. When pole is on negative real axis, overdamped. When pole is on negative real axis, overdamped. When pole is on negative real axis, overdamped. As long as the pole is on the negative real axis, and it will become the overdamped response. But here there are two poles at the same point. No, two different poles. Therefore, K is greater than 0 and k is less than k1. As long as this condition is satisfied, and your poles only lies on the negative real axis, and it should be a over damped response. It should be acting as a over damped response. And some of the students are asking, sir, why you should take this pole? Why you are not taking this pole? When k equals 0, this pole is on the negative real axis, but why you are not taking k is 0, you is taking k is greater than 0? Yes, that is a very valid question. But this is one pole and this is another pole. In these two poles, which pole is important? This is the dominant pole and this is the insignificant pole. So I concentrated only on dominant pole. Therefore, what is the answer? Finally the answer is k is less than k1 is nothing but 3.07 and k greater than 0. This is the condition such that the root locus diagram is over damped. Understand or not, students? Once again I am saying, when k equal to 0, pole is at origin, but over damped response poles are not available at origin. Therefore, this position is shifted to the negative real axis. If it is shifted to the negative real axis, k greater than 0. Then k greater than 0, pole is on the negative real axis, over damped response. Okay. Next, when the root locus diagram is critical, this is very simple question, I think. Critically damped response. When the root locus diagram is critically damped. Now the root locus diagram is said to be critically damped. The repeated poles on the negative real axis. When the poles are repeated on the negative real axis, single pole, no critically damped. Now these two poles are meeting at a particular point. Now that particular point is called as the breakaway point. There the gain equal to k1, which means that when k is equal to k1, then the root locus diagram is critically damped, which means that k equal to k1, which is equal to 3.07, then the root locus diagram is said to be critically damped response. Next, when the root locus diagram is said to be over damped, over is closed. Now when the root locus diagram is said to be under damped response, when the root locus diagram is said to be under damped response poles are the poles which are complex conjugate and which lies on left hand side of S-plane. Under damped poles are poles which are complex conjugate which lies on left hand side of S-plane. Now the poles is stable and which lies on left hand side of S-plane. So when the poles is on the left hand side of S-plane, it should be having a real part, negative real part or positive imaginary. Negative real part, positive imaginary part, which means that complex conjugate poles. Is it right or not? Complex conjugate poles. Now when the poles are complex conjugate, and what is the range with respect to k1? When k equals 0, pole is on origin, no underdamped. When k equals 0, pole is on the negative real axis, no underdamped response. When k greater than 0, it is lies on the negative real axis, no underdamped response. When k equal to k1, repeated poles on the negative real axis, no underdamped response. So your pole should be in the air such that it is having a real part and imaginary part. That air is also only left hand side air, not right hand sided air. Am I not? So when the pole is on the takeoff position, the pole is on the takeoff position when k is greater than k1. When k is greater than k1, and as long as it is on the left hand side of air, then it should be always over damped response. So k greater than k1, pole is here, real part, imaginary part, real part, imaginary part, real part, imaginary part, and k is less than k margin. K is less than k margin. Therefore, when k is less than k margin and greater than k1, then the root locus diagram is said to be under damped response. Therefore, when k is less than k margin is 48 and less than k1 is greater than k1 is 3.07. As long as this condition is satisfied, then that root locus diagram is said to be under damped response. Okay. So now I hope you understand this, and you understand when the root locus diagram is undamped is not required because system is marginally stable, but all these are stable. When the root locus diagram is undamped means poles lies on imaginary axis only. When the poles lies on imaginary axis, the poles exactly lies on imaginary axis when k is exactly equal to k margin. Okay, it's not required. If you want also you can easily say. Okay, note down this. This is very, very important. So this is a very, very important question for the GATE examination point of view. For any root locus diagram, n number of root locus diagrams you will draw, and this should be the procedure of finding when the root locus diagram. But now I am taking with respect to breakaway point. Sometimes in the question is may ask with respect to break-in point. Assume that break-in point gain is K2 or breakaway point gain is K1, like that. If both are existing, sometimes he is asking about both. So take the 2 points and according to that you will find the relations. Okay. And when the root locus diagram is said to be undamped. So when the root locus diagram is said to be undamped response. This is very simple question, okay, but already system is, the root locus diagram is undamped only when the poles is exactly lies on imaginary axis. So your root locus branches is intersects with imaginary axis when k equal to k margin. So is 48, then the root locus diagram is undamped response, system is marginally stable. But this is not required because he is asking only with respect to K1. Tell me the relations with respect to K1. So underdamped, overdamped, critical damped, all are stable responses. That's why the stable I am taking, this marginally stable is not at all required. Okay. Now this is the first problem and we have to completed all the questions in the first problem. Then the students are raising some doubts in the second problem. The second problem is nothing but adding a finite zero. Once again I just repeat the problem where you are having some doubt. I just redraw the circuit. Okay. Then one point you have some doubt or asking, no? That doubt I will clarify. Now the same problem, right? One pole is at origin, one pole is at -2 and one pole is at -4. Now this is the root locus branch. This is, oh sorry, this problem. one problem, -1 and -2. Yes. Now this is the root locus branch, right? Now centroid sigma is -2.5. Therefore here I just take a 2 angle of asymptotes, theta A1, theta A2. Already the same problem which we already solved. Okay. Now there is no doubt, students, the root locus diagram starts with k equals 0, starts with open loop pole. As k is changing, this is not pole, this is 0. Now as k is changing, closed loop pole is moving, and the root locus diagram terminates with k equal to infinity, terminates with open loop 0. And the students are asking that, sir, as there is no root locus branch here, as k is 0, the root locus diagram starts with open loop pole. As k is 0, the root locus diagram starts with open loop pole. As k is changing, closed loop pole is moving. As k is changing, closed loop pole is moving. The students are asking that, sir, this is the intersection point, why you are not living here? No, who says that? This is the intersection point is only for drawing the angle of asymptotes. You have to leave or you have to enter. First you will meet. That meeting point is nothing but a breakaway point or break-in point. So you have to calculate the breakaway point. Now this is the problem, right? What is the problem? This problem is nothing but g of s, which is nothing but same problem, k by s into s plus 2 into s plus 4. I just add one finite 0 here. I just add one finite 0, which is s plus 1. If you find the breakaway point, you know the procedure of finding the breakaway point. If you do the same procedure, characteristic equation, k function of s, differentiate k with respect to s, find roots. If you do that procedure and you can get the breakaway point and you solve that one, the breakaway point you are getting s equal to -2.9, you are getting this one. That is the reason why. What is the breakaway point? At that particular point, two poles are meeting. So as k is changing, closed loop pole is moving, and these two are meeting at a particular point. That particular point is called as breakaway point. That breakaway point is -2.9. That's why this is the breakaway point. Leaves the real axis with an angle of plus or minus 180 degrees by 2. Now -2.9 is greater than -2.5. That's why this is centroid, this is breakaway point. Now after leaving, then it will follow the angle of asymptote and terminates at 0. And after leaving, it will just follow the angle of asymptote. Right? Terminates at 0. Now the root locus branch terminates at k equal to infinity, terminates with open loop 0, terminates with k equal to infinity, terminates with open loop 0. And here, this is centroid. This is the centroid sigma. This centroid sigma is -2.5. And this is the breakaway point. And this breakaway point you already calculated. You know the procedure. Now that breakaway point you can get s equal to -2.9. That's why you go to here. Okay. Now this is the one doubt why you are writing here. This is the intersection point. Centroid is the intersection point of angle of asymptote. It is just a point where you have to start drawing the angle of asymptote. But where you want to meet, where you want to leave the real axis, where you want to enter the real axis at a particular point, that particular point is nothing but a breakaway point or breakaway point and break-in point. Now that particular point is must and should lies on root locus branch. Then the students are asking a question that, sir, this breakaway point, this centroid, both always lies on the root locus branch or not? This is the root locus branch. -2.5 is on the root locus branch. -2.9 is also because this is the root locus branch. Students are asking, sir, this is the root locus branch. Therefore, this is the root locus branch. Centroid is on the root locus branch and breakaway point is also on the root locus branch. So you come to here. This is centroid. Centroid is on the root locus branch and again breakaway point is also on the root locus branch. This is the correct statement, sir? So that whether the centroid and breakaway point must and should lies on the root locus branch? No, no students. The breakaway point, the break-in point must and should lies only on the root locus branches. But centroid sigma, it may on the root locus branch or may not be on the root locus branch. Okay, there is no need, there is no guarantee, there is no necessary of root locus, the centroid must and should be on the root locus. No, the centroid may be anywhere, because the centroid may be, the students, now these two problems you may observe on the left hand side of S plane, but the centroid may be on the right hand side also. The centroid may be on the positive real axis. The centroid lies anywhere on the real axis. It may be on the root locus branch or it may not be on the root locus branch. Whereas the breakaway point and break-in point must and should lies only on the root locus branches. Understand or not? Now, this is very, very important. Okay. Now you just take this one. Okay. Now all the problems are similar. Almost we will complete all the questions what he is asking. Then we will solve the different kinds of problems. Okay. Note on this.